So this chapter 5, as we have learned in chapter 4, the chapter 4 was solely dedicated to closed systems. And in closed systems, we specifically focused on energy analysis. So the closed system, we had the specific focus on energy analysis of closed systems. When we're talking about chapter 5 is a chapter which is dedicated to open systems. The whole chapter is dedicated to open systems. And in addition to energy analysis for open systems, since there is mass flow taking place, you'll also perform a mass analysis. So there will be two analyses, these two analyses that would be encountered in this chapter. And this chapter basically deals with open systems or control volumes. The specific details of the chapter, the topics that we'll be covering is as follows, and it includes, we'll basically start with the conservation of mass principle. Just like the energy principle, we'll try to develop an understanding for the mass principle, conservation of mass principle. And based on the conservation of mass principle, we'll try to evaluate two kinds of systems: the steady state system and the unsteady state systems. That means systems in which there is flow taking place. Obviously, since you're talking about control volume, so there is flow taking place. But in one of the systems, which is the more generic type, with regards to time, there is not any change in the properties of the system at a specific location. So with regards to location and time, for a specific location with regards to time, there is no change in the properties. Unsteady flow, which is a rather not very easy to analyze systems, and they are rather more complex systems, they will expect a special category of these systems would be discussed. Uh, Once we follow the mass principle, or once we develop the mass conservation of uh, mass principle, we will try to apply the first law of thermodynamics, which is essentially the energy balance equation, as the conservation of energy principle to control volumes. So initially we will develop the conservation of mass principle for both steady and unsteady systems, and then we'll move on towards the conservation of energy principles and try to apply that on the control volumes as it has been specified in the previous slide. Now, when we are talking about the energy which is being carried by a fluid stream which is crossing a control surface, since you're talking about open systems, there is mass or fluid which is crossing the control volume. The total energy carried by such a fluid is basically summation of internal energy, flow work, kinetic energy, and potential energy. So we'll try to develop an equation on these four energy factors for the fluid. Furthermore, we'll also try to relate. We also are familiar with enthalpy, which is a combination property. So we'll try to incorporate in the energy balance equation the internal energy and flow work as a combination property of enthalpy. So once we are applying the energy principle to control volumes, we'll use we'll incorporate internal energy and flow work together in the property of enthalpy. We'll try to see how the equation changes when we do that. The significant part, the most significant part of this chapter is essentially the understanding of uh, common applications, the common applications or common uh, devices that basically work under steady flow condition. These are the engineering devices such as nozzles, compressors, turbines, throttling valves, mixers, heaters, heat exchangers. They are these are the components that are used in mechanical engineering, and they normally operate under steady flow conditions. So we'll try to apply the energy balance equations on these components and solve some numericals with regards to these specific components. We'll be individually dealing these components. Uh, if you're not familiar, nozzles are the devices that normally accelerate the velocity of the fluid. Compressors basically increase the pressure. Turbines basically reduce the pressure and utilize that pressure. Throttling valve is something that we'll come to know. It basically is used to bring down the pressure while keeping the enthalpy constant. We'll see of it. Mixers, heaters, and heat exchangers, again, these are the devices that we'll be studying in light of the energy and mass balance equations that we'll develop in the initial half. Moving on, we'll also apply the energy balance to a general unsteady flow process where the particular example case would be that of uniform flow, which would be the model for commonly encountered charging and discharging processes. All right. So this is basically the summary of what we'll be covering in this chapter. G, is there any question?
No, sir.
Oh, all right. So let's move on and try to understand the conservation of mass principle. So it says that mass, like energy, is a conserved property. So just like energy is conserved, it cannot be created or destroyed. Mass is a conserved property. We'll see the specific case where we see interrelationship of mass and energy, but this is the reality that mass, just like energy, is a conserved property. Uh, for closed systems, you are not interested in mass balance. Before that, so it says that if you have 2 kgs of hydrogen and 16 kg of oxygen gas and they react together to form water, they will form water having an specific the weight of 18 kgs. It is not possible that you react 2 kg of hydrogen with 16 kg of oxygen and end up having 20 kg of water, or rather 15 kg or 13 kg of water. Uh, Rather, there is a sense of mass balance associated with the process. You cannot have a process with mass being destroyed or created uh, unless there are some other reactions. I'll come to that in a minute's time. Specific reactions. So for a closed system, again, we are not interested in the mass balance because the mass of the system essentially remains constant during the process. So mass balance equation is not an issue. Excuse me. So mass balance system is not a mass balance equation is not a problem for closed systems since the mass essentially remains constant. For open systems or control volumes, mass can cross the boundaries, and therefore we must keep track on the amount of mass that is entering or leaving the control volume. That would determine how much mass is basically or how much mass gets associated with the control volume. Uh, the all-time famous equation that relates mass and energy is E equals to mc square, where energy is related to mass as a product of speed of light, square of the speed of light, which is 2.9 or roughly 3 into 10 to the power 8. This equation, where mass is converting into energy, is more often used with nuclear reactions where the slight change, smallest change in mass could result in a tremendous amount of energy, since it is multiplied by a factor which is at least uh, square of this term, 10 raised to power 8, 3 into 10 raised to power 8. So if you have a square of this term, you know how much big the value of energy could become for a small change in mass. On the contrary, the mass change or mass change with regards to energy change, it's a very insignificant factor. So in a reaction, the energy change, the mass change due to the energy change is essentially negligible because you'll have to divide it by such a large number of factor. So essentially it becomes negligible. All right, moving on, the conservation of mass principle, it says that if you have this bathtub as your control volume, so this is the bathtub which is your control volume, and you have mass flowing into the system, and there is a drain where the mass is flowing out of the system. So the mass which is coming into the system is 50 kgs, and the mass that is moving out of the system is 30 kgs. As a result, there would be some mass that is stored within this control volume, and the change in mass of the bathtub would essentially be equal to mass that is coming in minus the mass that is going out, which is essentially 20 kgs. But this information is not enough for me. It is essential that I am aware of the time for which this process has taken place. So the conservation of mass principle says that total mass which is entering the control volume during the time delta t, so you are referring to specific amount of time, minus the total mass which is leaving the control volume again during the same time interval is essentially equal to the net change in mass of the control volume specifically for that time interval. So you cannot just write that total mass entering the control volume minus total mass leaving the control volume is equal to net change of the mass. You have to specify the time for which that mass has been provided to the control volume, or mass for the time for which the mass has been leaving the control volume. Again, uh, the conservation of mass principle, the net mass transfer to or from a control volume during a time interval delta t is equal to the net change. It could be increase or decrease in the total mass of the control volume during the time interval delta t. Or you can write mathematically that mass into the system minus mass out of the system is equivalent to the change in mass of the control volume. Now, this change in mass of control volume basically refers to the difference between the final and initial mass. Initial means the mass at time t equals to 0 in the control volume, and final means the mass at time t equals to t. This is the two time states at which you are considering the masses of the control volume. So that means it is referring to the mass change for the time interval of delta t. Uh, since time is an essential parameter in conservation of mass principle, normally you express the mass balance equation in terms of mass flow rates. That means you express that the mass that is flowing into the system by m dot n, so the rate of mass flowing into a system minus the rate of mass which is flowing out of the system, m dot out, is essentially equal to the rate of change of mass of the control volume. This is basically the most familiar form of the equation. Now, can you tell me in terms of let's say if I have this pipe over here, and this is the cross-sectional area of the pipe. There is some fluid which is flowing out of the pipe. Uh, the area of this cross-section is, let's say, AC. The velocity is V average, and the density of my fluid is, let's say, rho. So can we express the mass flow rate in terms of these three factors?
Yes, sir.
How?
Sir, mass can be given as density multiplied by the volume, total volume that we have.
Mass flow rate. We are talking about mass flow rate. Kgs per second. Mass flow rate is essentially equal to density multiplied by velocity, which is average velocity, multiplied by the cross-sectional area. So if you look at the units, this is kg per meter cube multiplied by meter per second multiplied by meter square. So this would cancel out, this would cancel out, and you'll essentially have kgs per second as the mass flow rate. Is it clear?
Yes, sir.
Got it. The important thing is that mass flow rate, as I mentioned, is equal to rho V average AC, the cross-sectional area through which the fluid is flowing. Average velocity, from your knowledge of fluid mechanics, you must have known by now that when a fluid is flowing within an enclosed tube, at the periphery, at the interface, the velocity is essentially zero, and the velocity is maximum at the center. So you have this sort of a profile for the velocity profile in a fluid at no slip condition. So in such a case, basically you take the average velocity, which represents the complete velocity of the fluid. That is the average of the maximum and zero. This is V average. Now, this is the mass flow rate equation, where mass flow rate is density into V average into AC. Do you know what is this term V average into cross-sectional area?
Volume flow rates.
Very good. So this is essentially volume flow rate, which is meter cube per second. And so you can write your mass flow rate as, or since you have this as the volume flow rate, you can write your mass flow rate as density multiplied by the volume flow rate, or volume flow rate divided by the specific volume, because density is 1 over specific volume. I hope it is clear so far.
Yes, sir.
Yes, sir.
All right. Now, mass balance for steady flow processes. Mass balance for steady flow processes. Again, you are talking about steady flow processes where the total amount of mass which is contained within the control volume, it does not change with time. So mass of control volume is constant. The only difference is, all right. So the within the given space, the mass of the control volume is constant. That is steady flow process. With regards to time, the conservation of mass principle requires, it then requires, if the mass of the control volume remain constant with regards to time, it means that the total amount of mass which is entering the control volume should be equal to the total amount of mass which is leaving the control volume. Is it clear?
Yes, sir.
All right. So for steady flow processes, we are interested in amount of mass flowing per unit time. That is the mass flow rate. And for multiple inlets and exits, where you have multiple inlets and exits to the system, you know that if the control volume mass is not changing with regards to time, uh, you will essentially have the mass flowing into the system, summation of all masses flowing into this mass flow rates into the system is equal to summation of all the mass flow rates out of the system, since the mass is not changing. The interpretation is this, that if you have an inlet through which 2 kg per second, the first inlet is where the fluid is coming into the control volume at the rate of 2 kg per second, and the second inlet is where the fluid is coming into the control volume at the rate of 3 kgs per second. If the mass of control volume is not changing with regards to time, that means whatever is coming into the system at whatever rate, it should exit the control volume at the same rate. So the total mass flow rate at the outlet would essentially be the mass flow rate 1 plus mass flow rate 2, which is essentially equal to 5 kg per second. Is this clear to you?
Yes, sir.
Yes, sir.
All right. Now, most of the engineering devices that you'll encounter, whether it's turbine, it's compressor, or nozzle or diffuser, they normally are single stream devices. That means they have one inlet and they have one exit. In such a case, the mass which is flowing into the system at the inlet is essentially equal to mass that is flowing out of the system. Or in other words, the rho, velocity, and area combination of these three, the product of these three at the inlet should be equal to the product of these three properties at the exit. I hope this is clear. As
Yes,
it
sir.
is mentioned that many engineering devices such as nozzles, diffusers, turbines, compressors, pumps, they involve single stream, one inlet, one outlet. So they basically follow these two equations for, again, a steady flow process, since we are dedicated this slide to steady flow process. A special case of a steady flow process is the incompressible flow. Incompressible flow is a flow where your density is essentially constant. Incompressible materials or substances are those materials where your density essentially remains constant. It does not change with the process. And this is specifically directed to the case of liquids. Liquids are normally incompressible. Their density does not change with the process. Ji, is there any question? Can you turn off your mic, please? Can you turn off your mic, please?
Right.
All right. Saad, kindly have your mic turned off, please. Anyways, so for the case of liquids, which is incompressible substance, density is essentially constant. In such a case where density is essentially constant, if you have steady incompressible flow, that means your if you're having a steady incompressible flow, uh, you would essentially be having, let's say you have summation of mass into the system is equals to summation of mass flow rate into the system, summation of mass flow rate out of the system. This is the mass balance equation for steady state process. If I have single inlet and single outlet, I would write it as mass flow rate into the system is equivalent to mass flow rate out of the system. And I can further write it as density at inlet, average velocity at inlet, and cross-sectional area at inlet is equal. Product of these three is essentially equal to density at outlet, velocity at outlet, and the cross-sectional area at the outlet. Now, if your density is constant, that means rho 1 is essentially equal to rho 2. These two would cancel out, and you would essentially have V1A1 is equals to V2A2. That means the volume flow rate at 1 is equal to volume flow rate at 2. This is that you derive if you have steady state flow and you have incompressible substance. This is the equation that you develop. Now, in such a case, that means for steady state incompressible flow, you will have the volume flow rate into the system is essentially equal to volume flow rate out of the system. Or for single stream, as I mentioned, you can write volume flow rate at the inlet V dot 1 is essentially equal to volume flow rate at the exit, which is essentially V dot 2, or V1A1 is essentially equal to V2A2. Now, this does not mean that volume is a conserved property. That means there is no such thing as the conservation of volume principle. This conservation is essentially related to the flow of liquids. In flow of liquids which are incompressible, the volume flow rates and the mass flow rates remain constant. And it is essential that you are referring to the steady state flow and incompressible substance. No such thing as conservation of volume principle. Let us have a look at an example. If you have an air compressor and let's say you are having steady state flow. Steady state flow means that you have one inlet and one outlet. So your mass flow rate at inlet is essentially equal to mass flow rate at the outlet. This is being governed by the steady flow. Now, air compressor, you know, in air compressor, density at the inlet would be less as compared to the density at outlet. So your density 1 should be less than density 2. Air would compressor would compress the air and increase the density. Uh, in such a case, if I write the uh, equation in this form, m dot 1 is essentially equal to rho 1, v1a1 is essentially equal to rho 2 v2a2. This equation is balanced equation and this is correct. But uh, if I combine these two terms together, this is essentially volume flow rate. And if I combine these two equations to these two terms together, this is essentially volume flow rate at the exit. If densities are not same, if density 1 is less than density 2, let's say density 1 is 5 and density 2 is 10, the volume flow rate cannot be the same. Is it true? The volume flow rate, for example, would be if it is V1 is 10, at the exit it should be 5. Only then you will have the mass flow rates to be the same. So volume flow rate, it is not essential for the volume flow rate to be constant or conserved in a steady state process. Is it clear? That's why you have different volume flow rates over here, since your densities are not constant. Clear enough?
Yes, sir.
Yes, sir.
All right. Now, we'll be looking into one more thing which we have already looked since we are moving towards the energy balance equation or the energy equation for open systems. I would like to recall the energy associated with the flowing fluid. You have seen this schematic a couple of times before, but I'll repeat it again or recall it again so that we get familiar with it. If you have this control volume with you, and in this control volume, there is a small chunk of element that has to get into this control volume. Let us have a look at this control volume over here. This is the control volume having a volume V and pressure P, which has to move into the control volume. It has to move into the control volume. That means the fluid behind it has to apply certain force so that this chunk moves into the control volume. The resistance to the flow is caused by the pressure of this chunk. And in order to overcome the pressure of this chunk of volume or flow element, the force that is needed to be applied by the fluid behind it, which is at its rear, is essentially pressure multiplied by the cross-sectional area, where this is the cross-sectional area of the uh, element. If this is the force that is being applied to move this small chunk into the control volume, uh, and we have to calculate the work done associated with this force, this whole volume, if it has to move into the control volume, it has to cover the length L. So the force has to be applied over a length of L so that this chunk moves into the control volume and the flow continues. In order to calculate the work associated with this, work done associated with this uh, flow, or to keep this flow going, work done is essentially force multiplied by the length for which that force has to be applied so that this volume moves into the control volume. The small element moves into the control volume. And force into length is essentially pressure into area multiplied by length, and pressure area into length is essentially the volume. So PV is the work done associated with the movement of this fluid into the control volume, and to keep the motion continuous or to keep the flow moving, this is the work done associated with the flow. And if we are talking about the specific energy or specific work done, it is essentially pressure multiplied by the specific volume. This is the flow energy associated with the movement of fluid into the control volume, or continuous movement of fluid into the control volume. I hope this is clear to you. Uh, I'll again show you the process. So you have this force is equivalent to pressure into area, and this pressure into area is basically resistance for this, which you apply a force, or the fluid applies the force. This fluid applies the force for a length of L. So your work flow essentially becomes PAL, or P into volume. And if you want to express it in per unit mass, you will have to express it by P into specific volume or pressure divided by the density. This is the flow energy which is associated with the control volume. I'll hold on at this moment and we'll move on and see how we can differentiate the flow in open system and closed systems, or how we can differentiate the flow energy and try to develop an energy balance equation in our upcoming class.